Hello and welcome back to Calculus 2, section 8.2 on integration by parts. Alright, so what is integration by parts? Anyone? Did you hear the stories? Or what would that be backwards of in terms of derivatives? What do you think? Yes?
Is it when you solve for u?
Well, that was the back substitution. That was the back substitution. And product rule, yes. So, the chain rule from Calc 1 has u sub as a backwards procedure. Product rule from derivatives from Calc 1 will have integration by parts as a backwards procedure. So today we're going to explore that one, and to derive the formula we are going to start with product rule, right? Now some of you had the formula with u's, some of you had the formula with f, whatever, it doesn't matter. So in general what you had is that the derivative u and v are functions of x. I will just write u and v. So derivative of u times v, that's a product rule, was uv prime plus vu prime. So this is the formula which you memorized and used it for as a product rule. So I'll box this and say product rule. Now, what I'm going to do is rewrite this as dv dx and du dx. So, we have ddx of uv, that's the derivative, is equal to u dv dx plus v du dx. And now I'm going to integrate both sides in respect to x. Now, when you integrate in respect to x, you have three integrals to work with. So when I'll write this again and then integrate. So this line is important here, so I'm not going to touch that one. Really? So here it is, the same formula, and now I am going to integrate each one of these. Integral dx, integral dx, integral dx everywhere. And from the fundamental theorem of calculus, we know that integral and derivative cancel. Therefore, on the left-hand side, you just have u times v. On the right-hand side, dx will cancel dx, and dx will cancel dx, and you will have integral of u dv plus the integral of v du. And now we are going to solve for integral of u dv. So integral of u dv is equal to uv minus the integral of v du, and this formula is known as integration by parts, where your parts are going to be u and dv. So integration by parts. Now, before I jump in and do 7,000 examples, I am going to prove this formula in another way, graphically, as well. So if you have some function, whatever, right? And this is your u-axis and this is your v-axis, and you come up with some limits for integration. This function here, so this over here would be du, and this over here would be dv. So now, for this region here, I have that the area, call it area 1, whatever, is equal to the integral of the function v in respect of du, because your representative rectangle is du. The one on the other side of the function is, call it area 2, integral of, and now since you have the horizontal line, it is u dv. And the total area A, which is given as A1 plus A2, is u times v, because you have a rectangle where on x-axis you have 0 to u, and on the y-axis you have 0 to v. So u times v for the rectangle. And now, when you plug these two integrals where they belong, right, you will get that area is equal to A1 plus A2, which is reflected as uv is equal to the integral of v du plus integral of u dv, and you rearrange it again as integral of u dv is equal to uv minus integral of v du. And that takes care of integration by parts, solved in two different ways, right? You have the derivation done from the product rule, and you have the derivation now done from the graph. Doesn't matter which way you approach it, obviously, formula is formula. And now it's time for us to discuss the use of this formula. Obviously, it will be practice to spot when it's appropriate to use this. So I'm going to put a couple of examples to make sure that you see first where the need for this formula is. So I'm not sure if I'm going to have 3 or 4, so just, stick with this for a second. So we start with the basic integral e to the x dx. Then we're going to have integral of xe to the x squared dx. Then we're going to have integral of xe to the x dx. Well, I guess this is enough, because the next one I would put you won't be able to solve in calculus anyway. So there they are, right? 3 integrals, and right, they're very similar, right? They're very similar. What do we have for the first one? E to the x plus c. So that would be what we call a basic integral off of the chart of basic integrals. So we're going to say basic. Now, what's the next part? U sub. Perfect. And it's U sub because we have function derivative pair. Your function u is x squared. Its derivative is 2x. So put a half and a 2 in there, and you can work out the u sub in 2 lines. Now look at the third one. It looks very similar to the middle one, but it doesn't have that square. And this is where integration by parts kicks in. Integration by parts kicks in there because nothing else would work. It's not a basic integral, and you can't do integration by u substitution because your exponent is just x. If you say u equals x, then all you're going to do is change all x's with u's in the next step. So clearly, it's not a basic integral. Clearly, the u sub didn't work, and we can go and try using integration by parts. Now, I really need you to focus on this, not write. Just look at this. You can catch up with writing, or I'll post these notes anyway. Let's see how's this done. Integral of x e to the x dx. Now, the formula for us is integral u dv is equal to uv minus integral of v du. If you get this, you are done with this section, right? Then you can have anything. First of all, there are two parts, two players in the formula, player u and a player dv. Those are the two players. Those two players will take on parts of the integral. Now, clearly, dx is always a part of dv, but could be more than dx. So dx is always in here, but it could be dx with e, or it could be the whole thing, right? We don't know that yet. So the way to set this up is to say, I need u and I need dv. So those are the two parts that I need. Now, experience, homework, and, blood, sweat, and tears will eventually teach you what to pick, right? That's something that I don't get to teach, but you get to learn from experience, right? So now, if I pick u equals x and dv equals e to dx dx, now in the beginning, for all of you, clearly this is going to be trial and error. And when you make a wrong choice, you will immediately know, because you are going to get the worst problem, all right? Now, this is going to work out fine. And now you're going to see what happens when you make the right choice. When you make the right choice in by problem that is integration by parts, the new integration is easier or is possible. It's nicer. When you make the wrong choice, you will always make it worse. So that's how you know it's a wrong choice. But we'll get there. Now, clearly, for the formula part, which is on the right side, I need a u piece. I already have it. I need a v piece. Well, how am I going to get a v piece? Well, I can integrate this, and I can get a v piece, right? And then I also need a v piece, which I will get from here when I integrate. And I need a du piece. Well, you know how to get du from differentiating for u sub, right? So that means that I need a du over here. And what's the du? Keep talking.
Dx.
Yes, 1 dx. So just dx. Guys, this is your u sub right there, right? So if you're able to do u sub, you will be able to do this in a heartbeat. And now the new part is you have to integrate here to come up with a v. Integral of dv is v. Integral of e to dx is e to dx. Now I know that you are itching to put plus c, but we are not going to, because there will be a plus c at the end of the problem when we are done with everything, right? So I am not going to put this plus c here. I'm just going to integrate and leave it without plus c. So now I need to, so I used I hope you see that I used the problem compared to the left-hand side to create u and dv. I made those choices, and then I differentiated and integrated to create du dv. Now I need to compile this side. Pull your u. So now this problem here is equal to uv, so x times e to the x, minus integral v e to the x du is dx. So there is no way to do this without writing it out. You have to learn that part. Now I'm going to also give you a visual approach here. If you draw this arrow like this, it gives you the formula actually. Do we see uv? Do we see vdu? Right? So that arrow can help as a visual clue to what your formula is. So again, u times v minus v du. Now, did I make a good choice? Well, of course I did. Do we see that the only integral that I need to do is a joke, right? So that's how we know that the choice was good. If you make a wrong choice, you are going to get the integral that it's worse than the one you started from. That immediately tells you that you have to go back and revisit your choices, right? Just like life. It's the same, there's no difference, right? So x e to the x minus the integral, which is e to the x, and here's your plus c. And because I know we have computer science people in the classroom, you have to factor out e to the x minus 1 plus c, right? Because you want a simplified answer as much as possible. And that's that. So this is your integration by parts. Now, if you are to make a wrong choice and pick this to be x dx, the integral of x would give you x squared here. And then this integral would have x squared, where this one had x. So we made it worse. You see that? So when you see the integral in here being worse, you know that you made a bad choice. You go back and you fix that, and then you do it again. It should work out fine. The next example is going to be another example where we are mixing functions that are not compatible. What do I mean compatible? Well, if the first function here is a polynomial and the second function is polynomial, just FOIL the damn thing, right? There's no need for any fancy methods. You can use algebra to come up with one polynomial and then just integrate like that. There's no need for anything fancy. But when you have polynomial function and then transcendental function, what is the transcendental list of functions? Is, ln's, trig, hyperbolics. If you mix them, right, then this is your method. Because this method separates those into different parts to do different separate calculations, and that's why the method works when you start mixing different worlds. The next section 8.3 is going to be trigonometric integration. Well, all you're going to have is just trig everywhere. It's not going to be mixed with ease. It's not going to be mixed with polynomials. But because it's all of a kind, you don't have to use this sledgehammer, right? You will just use the U sub and, cool techniques, right? But as soon as you start mixing different worlds, polynomial with transcendental, or even the transcendental of one kind with another kind, then the U sub is what you need. Sorry, not U sub. The by parts is what you need to live through that. So here is another example. And I'm going to ask you to do this on your own because it is literally the same as the previous example. It's going to be integral of x cosine x dx. So you pick your u, you pick your dv, you calculate the ones underneath. If you want to put the cool arrow, you can. All right, that's more than enough time. We start with u dv, pick x, cosine x dx. Now we have du equals dx and v equals sine x because integral of cosine is positive sine. And I'm going to put the arrow which helps with the formula and have u times v is x sine x minus the integral of sine x dx, which is v du. So if you want me to write this out, Here's my u, here's my v, here's my minus, here's my integral, here's my v, and here's my du. So you can see that that line is u times v minus integral of v du, and I am picking those from the blue substitution part. And now I'm happy because I can easily integrate sine. So we get x sine x. Integral of sine is negative cosine, so plus cosine x. And then we have the plus c. Now we can't factor anything in this case, so we get to leave it this way and move away. Now let's say you care, right, and you want to check. What do you need to do to check?
Take the derivative.
Beautiful. Take the derivative of the answer. If you get your problem, this is correct. This is why I always loved integration as a student, right? Well, I was geek too, but that's different. Right? You can take the derivative and check every problem, which is why you can walk out, right, your first exam, just put 100 right here, right? Second exam, all integration again, just put 100. Because if you differentiate every, it just takes not to be lazy. That's all it is. And care, obviously. So don't care plus lazy or either or. You are not checking and that's it. But if you care and you're not lazy, here it is in green. The derivative of x sine x plus cosine x plus c. You do not have to include plus c. What's the derivative of plus c? Zero. C is a constant, right? So you don't even have to bother writing that. But okay, fine. So now the first part is the product rule, right? X times sine. What are my derivatives there? Copy the first, which is x, times derivative of the second. Derivative of sine is cosine x. And then plus copy sine x. And then derivative of x is 1. Plus, what's the derivative of cosine? Negative sine x. And then plus 0 from c. You see that these two drop, and the only thing that is left is x cosine x, which is what our problem was. And that's it. Every single problem, you could have done it earlier with e, and it will work the same way. Cool. So now, since we are on a streak, the next problem is going to be integral of ln x x ln x dx. There we go. Have fun.
You can't integrate it, right?
I don't know. I'm still looking through my book, but I don't know, like.
I thought it was.
I don't think you can.
So I didn't put that.
It's not what that's saying.
Isn't it 1 over whatever it is? Like, so it would be v is x dx,
So-
or the integral value x squared over 2. But then if you put dq into it, the x is cancelled one out of it. So I think it's
He wants to cause chaos.
I just wanted to see where it would end up.
Okay, so
That's
So, x to the second power
integral of ln x.
divided by 2 minus.
It is. It's 1
Anyone
over
know
x.
what the integral of ln x is?
It says 1 over x.
That's why what?
Derivative of ln is
No, that's the
I
integral of the
looked it up. It's like a
like
x
x
times
ln x.
Oh god, my brain.
I thought we were supposed to do that. No, he said we last class. It's not a simple integral.
Okay. Yeah. Right. I knew I wasn't losing my mind.
I should switch things around. Yeah.
Oh yeah. I think you're thinking of
But isn't v the integral? Or v is,
Like-
because you have dv, which is ln x, and then isn't the v the derivative of it?
No, the V is
Oh, okay, this way.
U
Let's try it
U
though.
is
Alright,
U, du is the derivative
X.
of U, and you're taking the integral of V.
Oh.
Which is why I'm sitting here like.
How'd I get that first one right? I got it right.
The derivative of ln x is just
So it's the integral of ln x.
I'm going to shoot.
v is gonna equal minus
Oh boy.
x squared divided by 2. I think the u was supposed to be ln x, and then the u is 1 over x. Yeah, x.
Yeah, it really is. It's
That.
gonna be. It's gonna be extremely hard.
TV.
Hit the brick wall yet?
No.
No.
Are you trying to cause chaos?
So it's just straightforward, right? So what's u?
ln x.
ln x, very good. So we cannot memorize that u is x and just try to solve every problem, because it doesn't work, clearly. You will know when you make a wrong choice. You will know quickly, right? So let's make a wrong choice. U equals x. dv equals ln x dx. And this should be enough, because once you go du equal dx, you go, I can't integrate ln, right? And you know immediately you made a wrong choice. Because we never learned the integral for ln x. So that can't be there. Then by process of elimination it has to be here, right? So ln x, and then stick an x right there. Derivative of ln x is dx, and the integral of x is over 2. And we don't have to put plus c, there will be plus c at the end of the problem. Now we draw our arrow, and we have what? We have x squared over 2 times 1 over x minus the integral of, no, sorry, that's wrong. It's x squared over 2 ln x, thank you. And then now is x squared over 2, 1 over x dx. You see, this dx is that one. And if you don't have it there, then you don't have an integral here. That dx is not for decoration, right? It's a part of the integral. It goes. Now we have 1/2 x squared ln x minus 1/2. And when x and x cancels, you just have x dx. Oh, when the things work out nicely, right? So we have 1/2 x squared ln x minus 1/2 x squared over 2 plus c. Now I am going to factor out 1/2 x squared. I'm doing this because computer science in the room, right? Otherwise I wouldn't care. 1/2 x squared, and what's left is ln x minus 1/2 and then plus c. So we have, right, 1/2 x, x squared over 2 and x squared over 2. We can pull that out, and the leftover is ln x minus 1/2, and then we have a plus c. You don't believe me? Go ahead, differentiate. It will work out, and we're done. What was the integral we couldn't do? ln x. All right, that's the next problem. We're almost done with a quarter of our lecture. Hang in there.
Use dv, so technically anything here is just 1 times ln x dx. Just take 1 and put that as du.
dv.
No. Oh, yeah, dv, I meant, yeah, dv. So keep ln as like the last one for having u, keep ln as u, but dv is 1. Yeah, so just still don't have to go through the complications of integrating. Everyone looked up the
What is U? So what's dv? dx. Good. 1 dx, but dx. Yeah. So du is 1 over x dx. And what's v? X. Hit this with the arrow. We have x ln x minus integral of x times 1 over x dx, which is x ln x minus integral of dx, yes, which is what? X ln x minus x plus c. We factor out x, ln x minus 1 plus c. And now you know what the integral of ln is. Derivative of ln is 1 over x. Integral of ln is x, open parenthesis, ln x minus 1. So this is your introduction to integration by parts. Why is it called introduction? Because these are the base examples. Why is there more? Because we can have nested integration by parts where you have to do a couple of these procedures in a row to solve a single problem. The number of integration by parts that you have to do for those nested problems will depend on the exponent of the x, because every time you do integration by part, the derivative will only peel off one exponent. Therefore, if that is x to the 4 cosine x right there, you are going to do 4 integration by parts to kill that x to get to the part where you can just integrate a single trig function and be done, right? Guys.
That would be the same if it were cosine squared x.
No, completely different story. Because cosine x is right here, it's not affected by differentiation, so
If the problem was x cosine squared x dx.
yeah, no, it's going to be a completely different situation. So it's just on x. So now we're going with the nested problems, where we are going to have, so let's put a title or something, nested integration by parts. Integral of x cubed. Now, what do you want? You want sine, you want cosine, you want e? E. And we can make it a little bit worse by putting e to the 4x, because we will just have to shovel constants around, but let's just put x. Your textbook will have e to the 3, e to the 7x or something like that. So that 7 doesn't change the procedure. That 7 will just appear as the annoying constant that will keep dividing. So you'll have, right, every iteration will give you another over 7. So you'll have 7, 49, and so on. But let's just keep the vanilla example. I have x cubed. That means 3 integration by parts in a row. to get all the way down to the solution. So we immediately start working. So, right, we're not sleeping here, right? U equals x cubed, dv equals e to the x dx. du is equal to 3x squared dx, and v is just e to the x. Put a little arrow there. And now we have our first x cubed e to the x minus, you can kick 3 outside of the integral and have your x squared e to the x dx. So this is better, but you still can't do it. So you have to do integration by parts again for the second, right, for the integral, and you will copy everything else. Let's go orange. U is equal to x squared, dv is equal to e to the x dx. du is equal to 2x dx, v is e to the x. And then we put our arrow. Copy x cubed e to the x minus 3. Now you open parenthesis, and now you do the integration by parts formula, which is x squared e to the x minus 2 integral of x e to the x dx, close parenthesis, equals. Now when you look at this, right, this integral here is still polynomial times transcendental function. Yeah, one more integration by parts, right? So that's going to be, let's go green. So we have u equals x, dv equals e to the x dx, du equals dx, and v equals e to the x. We put our arrow and we copy everything from the problem. So x cubed e to the x minus 3, open parenthesis, x squared e to the x minus 2. And now, oops, instead of integral, we open another parenthesis, and we have our green integration by parts, x e to the x minus integral e to the x dx, and close both parentheses. So now I am going to work this out, and be very careful when you start distributing. Please don't start with this 3, right? Because the 3 has to jump here and here, but not in these, right? So start working, from inside out. X cubed e to the x minus 3, open parenthesis, x squared e to the x minus 2, open parenthesis, x e to the x minus e to the x. So we are going to start by, rather than distributing everything, which you could, we can start factoring stuff. If we factor out e to the x, then e to the x will be with 2, and then you will be able to factor out e to the x, it will jump out with the 3, and then you will be able to factor e to the x for the whole problem. And just be left with a polynomial behind. So that's a cool cascade, I guess. So x squared e to the x minus 2e to the x, and in parentheses you're left with x minus 1. So I factored out e to the x into outside, right? So now I am going to factor out e to the x again. So this is x cubed e to the x minus 3 e to the x, and I'm left with x squared minus 2x plus 2. So these two puppies jumped out And now you have x squared, and then negative 2 times x is negative 2x, negative 2 times negative 1 is positive 2. Finally, you collect e to the x all the way outside, and you are left with x cubed minus x squared plus 2x minus 2, because you have, oh, lies, that's a times 3. So negative 3, positive 6, and negative 6. There we go. Much better. Plus c at the end, and call it a day. I mean, for the part 2 of the lecture, out of 4. Now, this was just a lot of nasty algebra. You could have multiplied everything out, distribute, right, and then collect like terms at the end, or you can collect like terms going backwards. Whatever you do, the last equation is the one you want to program in your software, right? That's the one you want to program, not the one on top. Count the number of operations in the last line, and then count the number of operations here and here, right? It's a huge difference, which is what makes your software faster. Cool. So now we learned that we can do nested by parts, right? Integration by parts. And that's going to come up later also in graduate school if you go take physics, graduate school, math, electrical engineering. You are going to see linear operators for differential equations like, what's the name? Thermal problems, and what else? Yeah, I'm blanking now on the name. But the linear operator, and generally linear operator goes either to the third or the fourth order. And when you have the fourth order linear operator, you have to do nested integration by parts. There we go. The other part where you are going to use integration by parts to solve problems is going to be differential equation Laplace transform. The formula in that course has integration by parts worked in. It's going to be integral of f of x times e to the negative st and then dt, right? So you will integrate that out and you will get a function in terms of s. But to do the problem, every time it's going to be integration by parts. So you're learning this also for later use in DFQ. I will be teaching integration. I will be teaching this Laplace thing about 2 months, so you can tune in that day and practice your integration by parts in a little bit trickier system because you have a variable t and you will have parameter s, and then that transformation changes the time domain into a frequency domain. Frequency domain are your hertz, so gigahertz and cycles per, it is cycles per time. So this is serious stuff. It's used a lot, right, in your future courses. And if you do have a STEM major, I'm not saying computer science probably won't see this, but all of you guys going to mechanical, electrical, physics, and if you're a math major, I mean, you'll be drowning in this stuff. So better know it. Part 3 of our lesson here is obviously definite integrals, meaning integral that has limits. You can compute a number at the end. but you have to use integration by parts. I'm going to steal a problem from homework for this one. Don't want to make it up because we can probably get a half decent solution if I pick something that it's given. Really? Not a single one? Nice. So word problem then. Good. All right. Part 3, definite integrals, right, with this. With IDP, integration by part. Something that is going to be very relevant to you. Problem 45. Region bounded by function g of x equals square root of ln x, and the x-axis on interval 1 to e is revolved about x-axis. Hey, this is you reviewing for your upcoming exam, right? Like a month or so. You pick the date, right? So it's a standard revolution problem, except now when you put the integral together, whether it's a disk or a shell, we're going to discuss that. But once you put this integral together, it's going to be integration by parts, obviously, right? So region bounded by g of x equals square root of ln x and the x-axis, right? On 1 to e revolved around x. So the first order of business is, what does the square root of ln x look like? And for that we have our dear friend Desmos, right? And then 1 to e, that's roughly 1 to 3, hoping that, you know, at e, it's going to be ln e 1, so yeah. So you plug in 1, that's 0, so 0 to 1 on a y. Okay. So we can quickly go Desmos. We click on Desmos, there we go. SQRT ln x, and that's what we have, right? Now we can also graph x equals e, hopefully. There we go. And the x-axis, if you want to see what the region that it's bound, is going to be y equals 0. And that's the green line on the bottom. So you have this shape, right, between 1 and the blue line, and then the green line, which is your x-axis, and the red line on top. So we are rotating on x-axis. So the graph we have starts at 1. It's going to do this. 2, 3. We have our E. So we are looking at this piece rotated on x-axis. So we have choices, right? We can do disk, we can do shell. Both of them should work, right, to set up. So if we want to do disk method, then we are going to use dx. So for the disk method, we are using dx. So we have volume is equal to pi integral. Now we need x values. That's 1 and e. That's what they gave us. And then we have our function squared, which is square root of ln x squared dx. And you see that we are getting pi integral 1 to e of just ln x dx. Now we know that we have to use integration by parts to solve the integral of ln x. But we did it already, right? So I can just steal that answer. I'll put integration by parts goes here. Because we did it, we are just going to steal the answer. And the answer was x ln x minus 1. And now you don't put plus c because it's a definite integral from 1 to e. Plug in e everywhere. That's e. Where's the pi? I ate pi.
Why do you hate pi?
All right. So we have ln e minus 1 minus plug in 1 ln 1 minus 1 pi ln e is 1, so we get e 1 minus 1 minus 0 minus 1. So this term dies and we just get pi. So the volume of the object that we got by rotation is pi. Ta-da. No. No, yeah, it is.
Or is it a cup?
It's a cool cup that fits a pie.
When you put it in a blender.
Yeah, it could be a blender cup, yeah. And that's part 3 of integration by parts done. One more. Now, what could that be?
Sine.
Very good. Very good.
And the others weren't?
So far, every problem was polynomial mixed with transcendental function, and you worked your way around it. You might already have a grasp of this, which is great. Now it's the time to involve another transcendental function. So we're going to have integral of e to the x times, let's say, cosine x dx. Remember the way you picked u and dv. If you had x to whatever power, you used to pick that as u because it gets differentiated and it gets killed off, right? Eventually. If there's only one x, one integration by parts. If it's 3 x's, 3 integration by parts, but eventually from x cubed to x squared to x and gone, right? In that ln problem we had, we couldn't integrate ln, so we picked ln as a derivative, but then it canceled with x, so it worked out. So we were lucky, right? It worked. Which one do I pick here as u, so it goes away with differentiation? And the answer is neither of them, right? What is the 100th derivative of e to the x? E to the x, right? And what is cosine going to do? It's going to flop between sine and cosine and then have that minus show up and disappear and show up and disappear, right? So neither of the two are going to go away, which doesn't fit anything we did so far, right? But then we're going to do it anyway, right? And this is one of those, right, cool problems where, you know, you just try and play with it and hope for the best, yes. So here is the setup. We can use the other way as well, right? And the du equals what? E to the x? Dx, yes, keep talking, good. And what's my v? Right? I heard sin x. Sine x. Yes. So now, when you put the stuff together, you get e to the x sine x minus the integral of e to the x sine x dx. We achieved, right? The achievement. So now what? Well, we're going to do it again and hope for a different outcome. That's oh, I would know. Just do it again. Why not? So u equals e to the x, dv equals sine x dx, and now we have our du to be e to the x dx, and v equals negative cosine x because integral of sine is negative cosine. And we're going to put our arrow there. Don't forget to copy the first term, e to the x sine x minus open parenthesis, and now I have negative e to the x cosine x plus integral of e to the x cosine x dx. Work out the algebra here real quick. E to the x sine x plus e to the x cosine x minus integral e to the x cosine x dx. And now let's look at the damage. How far did we got in our calculations? Right? What now? Can you tell me what's going on here?
It's getting worse.
It's getting worse. This and that thing are the same, right? Cool.
Why?
Well, we did integration by parts on the function that just goes in a loop, so it has to come back to its original previous self at one point in life. So that was that point in life right there. So are you ready for $1 million step? Now you've got to understand this, so you've got to see it. This line here is equal to this line here. So I'm just going to take this term and move it to the other side and add it to this. Something you have never done before. Let me write this before we come back and discuss that one more time. You know what I'm going to ask you now? When I ask you 3x is equal to 4 plus 8 minus 3x. How do you solve this? You add 3x to both sides, right? And then you get 6x equals to 12, and then you divide both sides by 6, and you get your x equals 2, right? You know that. Well, guess what? The other thing is no different at all. You're going to move this puppy, add it to this one, get 2 of these, and then divide both sides by 2, and you're done. Now, I want you to take a moment and realize that someone figured it out about 200 years ago, okay? So one more time, once they repeat, and there is a minus sign here, obviously, you need the minus, because if it's plus, they just want to cancel on both sides, and you get garbage. So we move this term by adding it to the other side of the equation, because there is an equal here, right? So this line is equal to the line on the bottom. We literally ignore everything in between. We don't need it anymore, right? So it's just top equals the bottom line. You add integral to the left side. It's going to create 2 of those and divide both sides by 2. And done. So the next line over here, and I told you it's the same, algebraically it's the same as this mess I did right there. So I'm going to now have the new line be 2 integral of e to the x cosine x is equal to e to the x sine x plus e to the x cosine x. Divide both sides by 2, and you have your problem e to the x cosine x dx. Oops, I missed the dx over here. Is equal to 1/2 times e to the x in parentheses sine x plus cosine x plus c. Done deal. Yes? I didn't multiply it by 2. I have 1 already on the left, and when I add another one, 1 plus 1 is 2. Because one of these integrals was on the left, the other one came from the right, and when you add them together, 1 plus 1 is 2 of them, and then I just divide both sides by 2 because the problem was just one of those equals. Right? They were both on the left, and then I divide by 2, and that's how I get the half on the right. And I pulled E as well, and added plus C to the mix. And that's algebra done on integrals. That's going to be on Wednesday. We're moving the terms. There's no difference, right? Moving the terms, there's no difference. When they say, oh, there's too many steps. Try this one. Try this one. All right, cool. Now we are done with integration by parts because you have all of the flavors of what we have here.
How often is this kind of problem going to come up?
Only if I decide to put it up. Otherwise, it doesn't. This is one of those that we put in under the category of flexing in mathematics. Because this can be solved in 2 lines using complex numbers. 2 lines, that's all it takes. Over here you have 1 page of calculation with a step that, would take some time to see, and right? So, to solve this problem using complex variables, remember how we said that you can write sine as e to the ix? What's the integral of e to the ix? It's e to the ix over I. Nothing, right? So if you have this problem and you don't have the constraints to do it in the what we call a real domain, complex domain destroys it like nothing. So I mean, here it's a second anyway, whatever. Same problem done in a complex domain, and you don't need anything past basic e to the ax, right? Because what's I? I is a constant, like it's square root of -1. So if you have your integral of, what was it? E to the x cosine x dx, you rewrite this as e to the x times cosine is e to the ix plus e to the negative ix over 2 dx. Multiply e to the x. When you multiply e to the x and this one, they add as exponents, right? So what you have is integral, or kick 1/2 outside. You have e to the 1 plus I x. 1 plus I is a complex number. This is like e to the 2x. There's no difference. And then you have plus e to the 1 minus I x dx. Solution is in the next step. E to the 1 plus I x divided by 1 plus I plus e to the 1 minus I x over 1 minus I plus c, and you're done. Integrated. 2 lines, right? So the more you learn, right, the more math you learn, you are necessarily making everything you learned before simpler, because every time, right, you generalize or you bring in more powerful concepts. This is way more powerful than anything we've seen before, because you work with extra dimensions. You're no longer constrained to x and a y, which is 2-dimensional space. With complex functions, you are working in a 4-dimensional space. You have 2 times more power, which is why solving problems becomes a joke when you know that stuff. And one of the most irritating things, obviously, when you're in a grad school is you have a real analysis course, which is like Calculus 70. It's just proofs, right? And they say, prove theorem, blah, 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 and then in parentheses say, cannot use complex analysis, right? Obviously, because if you use complex analysis, it's 2 lines. If you use real analysis, it's like 2 hours of writing carpal tunnel and losing the will to live. That's technically, right, the way it goes. So, you know, you learn these things as you go along. But that's your integration by parts. And as I said, yes, you are going to have, you know, minimum of 2 problems on your exam 2. You are going to have at least 1 problem. You must have at least 1 problem on the final. And then you are going to have a chapter of this stuff when you take, if you take differential equations, right? And those of you who go beyond will see integration by parts more often. Math majors, a lot of your graduate degree proofs will be integration by parts. So that's the way it goes. Now, for the class that we have, you must be able to do the basic one, then the basic one with limits, right? That gives you a number at the end. Be careful what goes for you, what goes for DV. If you make it worse, try to switch it around. And this is a cool one to know, obviously, because ln is not a basic, right? Once someone hits you with, what do you know? You pull this one out, right? Because they're definitely not going to know that. And finally, the nested problems. You do have nested problems. Did I see into the 4th power? I think I saw one of the problems in the homework. I'm not sure what's online, what's not online, but there's x squared, there's t squared, there's a t cubed, another square, another square, another square. Oh, and then there is this one. It says x to the 9 ln x. Do we panic?
Yes.
ln x is backwards, yes. It is still a single integration by parts because u is ln. Yeah. They do not go beyond 3. And I did 3 right there, right? So there is 2 in between, and all of the problems, apart from 1, are squared. So you will have to do double integration by parts a couple of times. So your exam, you will have a double one, and you have the basic one, right? Now, the rules stack up with other rules. I could create a new one, but I lost a problem which used 6 different methods to solve at the end, with some algebra called mathematical flexing. We talked about it, right? I could create a new one, because the way to create these problems is to work backwards, right? It's your job to integrate. I just differentiate, right? I pick a function and I differentiate it into a something, and then you have to work it out in integration, and if you hit the target that I had, it's correct. It's way easier to make these problems than to, right? Because I need to just write an expression, differentiate, and then you have to integrate it to do it backwards, right? It's not fair, right? That's it.